Okay, we're pleased to have our next speaker. It's Alfredo Chavez from
UNAM, Oaxaca.
UNAM.
Oaxaca, yeah.
Oaxaca.
Yeah.
He'll speak on Newton-Okounkov bodies and middle models for cluster varieties.
Yeah. Well, thank you so much to the organizer for the opportunity to give this talk in this event. So I'm presenting this joint work with Lara Bosinger, Mangwai Cheung, and Timothy McGee that was recently uploaded in the archive a couple of months ago. And yeah, so I'm going to discuss several topics: Newton-Okounkov models, minimal models, and cluster varieties. So let me start just with a short outline of the talk. Probably the most important work that inspired this work was done by Grassmannian and Kontsevich in 2014, where they did lots of things. And among those things, they generalized the polytope construction of a toric variety to the world of cluster varieties. So what does this mean? In general, in toric geometry, you start with some torus, and you start with some polytope, convex lattice polytope in some vector space, and out of this you build a toric variety associated to the polytope. So you build a projective compactification of your torus, and well, what they did is to replace this torus by some cluster variety, replace this polytope by some sort of generalized notion of polytope that lives in some sort of tropical space that I will discuss, and produce some minimal model of a cluster variety. And the aim is to reverse this construction. So if you were in toric geometry, it would be like asking you have like some nice toric variety, what's the associated polytope? This is an interesting thing. For example, if you're starting with a symplectic toric manifold, you can get this by a moment map. Here we're not going to discuss moment map. It's going to be more like in the realm of algebraic geometry. Well, we were also motivated by some applications we wanted to give. In some recent, well, in 2018, Rietsch-Williams constructed Newton-Okounkov bodies that I will shorten as NO bodies for Grassmannians, and they use mirror symmetry to construct this. And a problem was to describe them as some type of convex hulls, and our work actually resolved this problem. I will not have time to really explain this point so much, but it was one of our main motivations. And also we can produce some examples of some Newton-Okounkov bodies exhibiting something called the world crossing phenomenon in the sense of Escobar and Harada. Okay, so that's kind of the outline. I will mainly just focus on the goal, and the applications are going to be just like sitting in the back. So first of all, in order to define a pair of cluster varieties, we need some input that it's embodied in a quiver, or what it's called a frozen quiver, an ice quiver, which is some quiver with R vertices without loops nor two cycles, and a subset of vertices called the frozen vertices. And out of this data, we can produce this pair of cluster varieties, AQF and XQF, and they are mirror dual in the sense of mirror symmetry. Maybe some years ago that would just be a conjecture, and nowadays it's just a fact. They are mirror in some framework of mirror symmetry. And that's why I'm going to use this notation. If V it's one of those, then V check is the mirror, and it just swaps the cluster variety. So the mirror of A is X, and the mirror of X is A. There's a much robust statement in which this occurs as families as fibers in some family, mirror family, but I'm not going to discuss that. So what's the rough description of these spaces? We have to start with two dual lattices. Say N, rank R lattice, and its dual lattice M. Out of this lattice, I can build tori by just tensoring by C star. I'm sorry, there's a typo. So yeah. If I have a lattice, the torus associated to this lattice is just the lattice tensor over Z with C star. Okay, so this is just isomorphic to C star to the rank of L. Okay, and in which sense we are generalizing toric geometry? Well, this cluster variety are a union of such tori, of these dual tori, And well, I'm not going to give the whole description, but let me just tell that they are endowed by construction with a very nice atlas of this algebraic tori, where the vertices, where the tori I'm gluing together are parameterized by the vertices of a very specific simplicial complex associated to my initial input QF, which is called the cluster complex. I'll give an example in a second. And each torus has a preferred set of coordinates, which are called the cluster coordinates. So, for instance, if you're in the variety A, these are related to the cluster variables. And the way this tori glue together, it's also very precise, and it's given by the change of coordinates is given by the cluster transformations, which are also very specific class of birational maps between tori. So instead of recalling the whole definition, let me just give you an example, my running example for the talk. So if I start with a pentagon and a triangulation of this pentagon, I can define a torus in the affine cone of the Grassmannian 2, 5. The 5 is because I'm in a pentagon, and the 2 comes because I'm with polygons. I'm working with polygons. Which torus? Well, it's just given by the set of Plucker coordinates, Pij, that are non-zero. I mean, those points whose Plucker coordinates Pij are non-zero for every arc in S. So I have 7 arcs. So this defines a torus. Okay, and it also defines a quiver by some combinatorial recipe that works as follows. For every triangle, for every arc in my triangulation, I just put a vertex, and for every triangle, I put an oriented triangle like this. I could put an arrow here and here, but I can just ignore them because they will not change my cluster variety. So this is kind of the initial input I have to define my cluster variety. And well, how does it work, this gluing? I can start with an initial torus, and then I can think of an adjacent torus that it's obtained by just flipping one of these diagonals of my pentagon. And well, I know that this that the corresponding Plucker coordinates satisfy this relation, and this is the cluster transformation I'm talking about. So in general, I will have, like in this example, I will have 5 pentagons, 5 triangulations of the pentagon, and this will define 5 tori glued to each other. And what I obtain, it's actually the variety I obtain by gluing this tori. It's a subvariety of the Grassmannian that up to codimension 2, it's just the complement of this particular divisor. This is the divisor defined by all consecutive Plucker coordinates by the vanishing of the consecutive Plucker coordinates. And the union of this tori up to codimension 2 covers all this variety. And then I can speak that I have a cluster structure on this variety. Yeah. And I can think of the Grassmannian as a compactification, a projective compactification of this variety, AQF. In this case, it happens that both varieties AQF and XQF are isomorphic, and you can see the cluster complex here. The cluster complex is just the outside pentagon. Okay, so you can see there's a torus for each vertex of the outside pentagon, and well, it's an accident that I'm talking about pentagons, triangulations of the pentagon, and the cluster complex. It's a pentagon. For personal statistics, it's something more interesting. Okay, questions so far about cluster varieties? So that's my example of cluster varieties. If you don't know, you can just keep that in mind. Okay. So
I like this example in general. There'll be many of those.
That's correct. Yeah. Well, for Grassmannian 2N, no, but like for flag varieties and other varieties, I will consider that. Yeah, I will have like the cluster complex will have infinite set of vertices. Yeah. Okay, that's correct. Yeah. It's the torus. I mean, we have to be non-zero, and all these guys have all the triangulations have the outside arcs. So always the consecutive Plucker coordinates should vanish. So that's why I'm landing in this complement of this division. Okay. So what's a minimal model? Maybe this is not an algebraic conference, geometry conference. So I will just give like the workout definition. So the definition is here. So how do you get to this definition proposed by Grosshack and Kele-Konsevich? First, they show that any such cluster variety is a log-Calabi-Yau variety with maximal boundary. The maximal boundary will come into play next slide, but the main point of this this definition of a minimal model is that it's log Calabi-Yau. And for us today, this only means that I'm talking about a smooth variety that contains a torus as an open subscheme. And every torus has a canonical volume form, right? The I ds1 z1, which the zr zr. So this is like the canonical form in a torus, and the fact that it's log Calabi-Yau means that this volume form extends to my whole variety, and it's nowhere vanishing, and it has no poles. That's essentially what it means. And what's a minimal model? So a minimal model comes from this minimal model program that actually works with projective varieties. So this is kind of not the mainstream version of minimal models. This is inspired by the work of Ithaka in the 70s, who was working on his version of the minimal model program, just as Mori. But he also considered non-projective varieties. So I have to consider an inclusion of my cluster variety into Y, where Y is a normal variety, and V is open there. And this is a partial minimal model if the canonical form of V has a simple pole along every irreducible component of the complement of my spaces. Okay, and it's minimal if I'm already projective. Okay, if Y is already projective. Okay, so it's all about the volume form. And well, in geometry, you love to work with charts locally, so you essentially have to pick your standard volume form with your preferred coordinates in every torus and just check if whether in the compactification, the divisor that you put in your compactification, this volume form has a simple pole or not. Okay, and the main source of examples are obtained by letting the frozen variables vanish. So in this case, the frozen variables will be corresponding to these coordinates that contain all torus, and if I let them vanish, well, I obtain like some compactification of this guy, and of course this the divisors in this compactification have a simple pole, well, just because how my volume form is given. Okay, any questions so far?
So in that example, you let the those variables finish, you'll get the whole Grassmannian back.
Yes. Okay. Okay, so now this thing of maximal boundary allows me to tropicalize my cluster varieties. So any log Calabi-Yau with maximal boundary will have a well-defined tropicalization, and defined in this way. So what you have to work with is with discrete divisorial valuations on the function field of your variety. So what's a discrete divisorial valuation? It's just valuations of this form, order of vanishing along some divisor. Yeah, so you just have one divisor. You just consider one. So where's this divisor living? You have to think. You can swap your variety by a birational variety, and you compactify it or partially compactify it by adding some divisor. And then, since the two varieties are birational, they have the same function field. So you have the order of vanishing along that divisor will define a valuation on that function field in the common function field. And if the volume form has poles along that divisor, then it defines a point in the tropicalization. Okay, so this is very abstract, and maybe it's not the best definition. So let me just give an equivalent definition. But first, yeah, let me just say that we can also construct the real tropicalization by completion. So it's like a process. It's just analogous process of constructing reals from the integers. You first construct the rationals and then you complete, and like that we can obtain this real tropicalization. Or you can give another very abstract definition using dual intersection complexes and compactifications that I don't want to discuss. And the best example to keep in mind, it's just the trivial example where the cluster variety is just a torus associated to some lattice L. So in this case, the divisorial valuations are going to be given by the monomial valuations on my function field of my torus, and essentially it's just like the monomial valuation is it's just given by, you give me a character and a co-character. So the co-character is my, okay, so to a co-character I can associate a monomial valuation just by taking the dual pairing with that character. Okay. And in general, for cluster varieties, since these are union of these tori, we're essentially just pasting together this kind of tropical spaces. So essentially what you can have, you can think it's every torus, if you tropicalize, you get a copy of the lattice, and then each copy of the lattice is going to be glued to each other by tropicalizing the corresponding cluster transformation used to glue them, and that turns out to be just a piecewise linear isomorphism. So it's just a collection of lattices glued to each other by piecewise linear isomorphism. They are parameterized again by the cluster complex. So in my example, you can think like in each pentagon you have set to the 7, and you tropicalize the gluing map that I just wrote there, the Pluto relation, and this gives me a piecewise linear isomorphism of this lattice, and then my whole tropical space looks like five lattices set to the 7, glued by this piecewise linear isomorphism. Okay. Yeah, I have 5 vertices, and in each one I have set to the 7 because the dimension of my space is 7. Yeah. Okay. What I'm telling you, it's like this lemma essentially, that any choice of torus gives me an identification of my tropical space with the lattice I'm working with. Yeah. And also the real tropical space, it's just identified with a real vector space, and the whole tropical space can be just thought of as having my same atlas, but just replacing tori by lattices and cluster transformation by the tropicalization. So what's tropicalization? You change the product by a plus and the plus by minimum. Okay. So I will use this notation. I don't know if it's visible. If my cluster variety is a union of tori TL, then I will write B trop S if I think of this tropical space just as a lattice L. Okay, so I'm just choosing one of my representatives of my in my tropicalization, and I decide to work with that chart. So one of the most important conjectures in cluster theory, on the theory of cluster algebras and cluster varieties, is the Fogg-Boncharoff conjecture. They conjecture that the ring of regular functions of on my cluster variety has a canonical basis parameterized by the integral tropical points of the mirror variety. Okay, and I will come to an example of this and actually the main motivation for this conjecture. The facts are that this conjecture is false in general. However, Grossak and Kilkonsevich in 2014 constructed global functions, certain class of global functions on cluster varieties called theta functions, and they gave conditions, almost optimal conditions, ensuring that this conjecture is satisfied, and moreover that the canonical basis is given by the theta functions. Okay, so this, if you know a little bit about cluster algebras, this is just like some of these are just the cluster variables if V is of type A, and some other might correspond to different elements, like the ones coming from imaginary modules discussed in the last talk. Okay, maybe yeah. So that's kind of the picture. And for most of our results, we really assume that we have this decomposition, that my cluster variety has a basis of theta functions. And as I said just 1 minute ago, this property has been verified in various families of examples, and there are conditions that are verifiable that one can try to check in each particular example. So, okay, examples of this are, again, if I go back to toric geometry, where my torus with my cluster variety is just a torus, then I know that the character lattice gives me a basis of global functions on my torus, right? And the characters are parameterized by the dual lattice L star. And by this example, well, if I change here B check, I will put a L star here, and then I will obtain here what I'm written here. So in the trivial example, the canonical basis of functions is just the basis of characters. Okay, so if you want, this conjecture is just a generalization of the property that tori have a canonical basis of global functions given by the characters. Yes.
So you mentioned that this conjecture is false in general. Do we expect it to be true on sort of cases that are generally interesting?
Yes. We expect that it's true in most of the interesting cases, but there are like also super interesting cases for where it's false, like the Markov cluster algebra related to the Markov numbers and things like this. So I mean, besides that example, I don't know if in the audience they know another very important example where this conjecture is not satisfied. But yeah, the feeling is like most of the varieties arising in representation theory, say, do satisfy this conjecture. Yeah, you're welcome. Okay, so in the example, you can also give a very concrete description of the theta basis. So these are the theta functions, and why, I will not say why, but I mean, it can be described quite explicitly in some cases. Okay, so let's go back to this picture. We have a cluster variety replacing my torus. Then I want to replace this notion of polytope to produce some sort of compactification of my cluster variety. And the main definition is this, and it's given by Gross-Haking, and Kontsevich. So if we suppose V has a basis of theta functions, its ring of regular functions has a basis of theta functions, then we can construct the structural constants associated to this basis. Namely, if I take two basis elements, theta p and theta q, then its product, it's again a global function. And since theta functions are a basis, it's a linear combination of theta functions. So this gives rise to these structural constants parameterized by the two elements I'm multiplying and the elements I'm using in my linear expansion. Okay, so these are just some complex numbers. It's shown that they are actually positive integers in general, or well, those that are non-zero. And using this fact, Gross-Haking and Kontsevich define what's a positive set inside the real tropicalization of the mirror. So why the mirror? Because I'm using the mirror to label the theta functions. Maybe I should have put in here a v. These are theta functions on v, and they're parameterized by the integral tropicalization of the mirror. So, okay, this is the definition. Let me just spell out. I have a set P that I should think as a polytope P. I take two of its dilations, positive dilations, say AP and BP. A and B are positive integers. Yeah? So I just dilate my polytope in A and in B. Then I take an integral point in that dilation and an integral point in that dilation. Okay? And then I'm asking that every time there's a theta function in these linear expressions for P and Q, then this label R, it's in the A plus B dilation of my polytope. So what if I'm just working with characters, this means like if I have a polytope and I say an A dilation and another polytope and another dilation, and these points correspond to characters, then the product of these characters correspond to an integral point that it's in the A plus B dilation of my polytope, which is just trivial statement. Yeah. So this is just generalizing the say how you can see multiplication of characters using the dilations in my ambient real space. Okay. So another way to just reframe this definition is that any such set just gives me a graded ring, a graded subring of this ring. So I'm dealing with regular functions, and I'm using the x just to know in which dilation of my polytope I'm working with, and the fact that that theta functions in this parameterized by this positive set satisfies this condition, just tell me that this is a graded ring. Yeah. So another way to think about this condition, it's just like a way to encode graded subrings of this ring. Okay. And the theorem, it's actually this motivation. They prove that when I have a top dimensional compact rational positive polytope, what does it mean so it's polytope. I mean, if I work in one identification of these vectors of this tropical space given by a lattice, then I can just think I'm working in R to the n. Then I can just draw a polytope and ask if it's whether it's positive or not. And if it's positive, rational, compact, and top dimensional, then the projected variety associated to the corresponding graded ring is going to be a minimal model of my cluster variety. That's what this theorem is telling me. And moreover, well, that's the important content of the theorem. I also have a toric degeneration that degenerates my cluster variety to a torus, and the compactification to the toric variety associated to that polytope. Okay, so somehow the picture I'm using to compactify the cluster variety can also be thought as a picture used to produce a projected toric variety, and I can degenerate one picture to the other using many parameters. This is multi-parameters, so I can deform my ring using many parameters to from this ring reach to this ring, and so that this variety collapses to this torus. Okay, so that's how somehow the picture. So the aim again of my talk it's to reverse this construction, namely given an open inclusion of a cluster variety into a projective and normal variety Y, I would like to construct the corresponding positive set. And second, when this is possible, then show that this is actually a Newton-Okounkov body. Okay, so let me now discuss Newton-Okounkov bodies. There any questions so far? No. Yes. Yeah. That's going to be an example. Okay, so first of all, what's a Newton-Okounkov body? Given Y, just like the Y's I was discussing before, d-dimensional variety over C, I can actually work over any other field, but maybe algebraically close. But I will just focus on C today. If I have a valuation, like not to the integers, but like to set to the D with some total order. So this is just like some kind of math satisfying all the definition of valuation, and I fix a line bundle, then I can consider the section ring associated to this line bundle. So essentially, this is the okay. Maybe I should say here RKL. It's just this global sections of R tensor with itself k times. So associated to every such line bundle, there's a graded ring that, if my line bundle is nice enough, recovers like some homogeneous coordinate ring for a certain embedding of my variety. Okay, and the Newton-Okounkov body, it's just given by this formula. So what I have to do is consider k graded piece of my section ring, consider the valuation, and normalize by k. So if I were like in this polytope, I mean in toric geometry, these polytopes actually determine basis of sections of these graded pieces. And what I'm trying to do, it's like I'm building a cone out of it, and I'm normalizing everything to level 1. Okay, then I take convex hull of that set of points and close it. So this is a closed set. Okay. I cannot discuss too much about these NO bodies. Let me just say that I mean, there's lots to say about them. That they just generalize both the Newton polytope of a Laurent polynomial and the polytope associated to a polarized cluster variety, toric variety. They were introduced by Okounkov just to develop some asymptotic theory of linear series associated to divisors. So there's some idea here, like there's some asymptotic behavior that one wants to study, and they're actually this was in the 90s, probably late 90s, and in 2009 and 12, Lazarsfeld and Mustata, independently Kavik-Kovansky, initiated a systematic study about these Newton-Okounkov bodies and how they codify geometry of the variety I'm starting with. And in 2013, Anderson used them to construct one-parameter toric degenerations of Y. So it's like the story was pointing out about the toric degeneration, but with a single parameter. So in our paper, we also want to compare like these two approaches of Anderson and Gross-Hakin-Kiel-Kontsevich, giving toric degenerations out of a Newton-Okounkov body. Okay, so these are just comments, just to get a feeling of why. Okay, so let me just go to the main point of the talk, or to the main theorem. So first of all, in order to construct these Newton-Okounkov bodies, I need various things. I need a variety Y, that is going to be a partial minimal, a minimal model of a cluster variety, and a valuation. So valuations we can use the cluster structure to compute these valuations. In order to construct cluster valuations associated to the cluster structure, in order to be able to do so, we need that this matrix that I'm defining here has full rank. So this is just like the sign incidence matrix of the quiver. So it's just like the adjacency matrix, but with signs. Like, well, just the ij entry is just given by the difference between arrows from I to j and arrows from j to i. And Fujita and Oya proved that if I'm in full rank, then I have a cluster valuation that has this property. For a theta function parameterized by the point m, the valuation is minus m. Some experts might be a little bit like shocked by this sign. It's because I'm working with the mean tropical space and not the max tropical space. So anyways, just to say that there's like a valuation, like a nice set of valuations constructed by the using the cluster structure. And in the recent paper, we also show that we can. So this is the case where my variety V is A of A type, and in our paper we kind of also focus on the X side of the picture. Okay, so we also need some hypothesis. We don't need the full rank hypothesis, but we need the full Fock-Goncharov conjecture to hold through. This remark is going to come back at the very concluding remark. So just like maybe a quick example of how the combinatorics can be used to construct these valuations. So somehow these are the valuations of some of these Klucker coordinates. I will not have time, but let's say that you can use combinatorics to compute these valuations. Here you would use like equivalent trees dual to this triangulation and use that to compute these valuations. Okay, so these valuations are again a big topic in the theory of cluster algebras. So okay. Okay, so how I'm going to construct these Newton-Okounkov bodies associated to this compactification. First of all, I will assume V satisfies the Fock-Goncharov conjecture, and then I will find fix a partial minimal model V of my variety Y, of my variety V, and I will let V1 to Dn be the irreducible components of the boundary of the complement between my varieties. Okay, then because this is a partial minimal model, Y is birational to V. And these di's are divisors there. So I can compute the order of vanishing along these divisors in the function field, and this will define valuations of my function field of my cluster variety. So by definition, they are points of my tropicalization of my variety V. Okay, and these are global functions. So since I okay, maybe I should put here that V check satisfies the Fock-Goncharov conjecture, so that to every point in my tropical space there's an associated global function. So here there's a type where it should be V check. If that's the case, then I can just consider this canonical function associated to my compactification, just the sum of all the theta functions parameterized by these divisors, these valuations I'm associating to each divisor. And I will call that the theta superpotential associated to the partial minimal model. Okay. So that's my main tool to start constructing subsets of my tropical space. I will say that my partial minimal model has enough theta functions if all the set of points in the tropicalization parameterized by setting this superpotential, by tropicalizing this superpotential and make it bigger to 0, is a basis of functions on the compactification. And the remark is that this gives sufficient that GHK already gave sufficient conditions ensuring this property. So what you should think about is like this cone, just like in toric geometry, is parameterizing the set of functions that are well, the characters that are extending from my torus to the compactification. Yeah, so this is just like some replacement of the cone associated, say, to an affine toric variety. Okay, so my example, back to the example, then this can be generalized to Grassmann Kn or n minus Kn with n bigger than k. Rietsch and Williams showed that the X variety can also be compactified by the Grassmannian, and say like the complement of the anti-canonical divisor I was considering is up to codimension to an X variety. And in this case, the divisors are very explicit, and the superpotential, each term is given in a very explicit way. And actually, this superpotential was already introduced in the context of Grassmannians by Marsh and Rietsch, and Shen-Wang verified that actually this is the zeta superpotential. Yeah. So this is my first example of the superpotential. The second example is actually a paper given by Tim McGee. So if I'm working with SLN and I consider G mod U a base affine space, then Y can be thought of as a partial minimal model of something called the double Grua cell described here. So it's just a cell inside the base affine space construct from this from a Borel subgroup and its opposite. And in that paper, McGee showed that actually the Gelfand-Tsetlin cone associated to this framework, it's actually unimodular equivalent to the theta superpotential cone. Yeah, so I mean, it's not so easy to explain in a 45-minute talk, because I mean it's a kind of long paper, this one. Okay, so finally, to reach my theorem, I'm almost there. I need to talk about some other varieties that we can construct from cluster varieties.
Sorry, other types, this was generalized relativity.
Besides A type?
Yeah.
I don't know if anyone has looked at this. I don't know. Yeah, there are Schumann, Schumann, Volker-Jens, and Koshiboy. Gleb Koshiboy. Yeah, they have lots of papers. Maybe in one of those they treat the other types. Yeah. Okay. So let me go back to this kind of matrices that I was discussing before. Before I was discussing this rectangular matrix formed by the quiver. Was then if I just try to build something that would look like a square matrix, this part and this part will be given by my quiver. And if I build matrices where I'm able to put whatever I want there, I can consider families of maps. These define families of maps from my A variety to my X variety, called cluster ensemble maps. And they actually define two things: quotient, a geometric quotient of my A variety, and a fibration of my X variety over the dual torus. And this is nothing like really nothing to be scared about. I mean, at the lattice level, I have H goes to the kernel. That's a subset of here. So I have H associated sublattice of this. By tensoring by R, I have an inclusion of the torus associated to N to H to the torus associated to N. And by diagonalizing this map, I have a map from M to H dual, and I have a map from Tm to Th dual. And the cluster variety A, it's just a union of these guys. And the cluster variety X is a union of these guys. So the statement is like, for every seed, I can have such a maps, and I can glue them together to build. I mean, this is acting by inclusion. This action extends relatively to every inclusion, and this map extends relative to the base. Okay. So I have this geometric quotient. It also has an atlas of tori parameterized by the same cluster complex. And well, this map here, it's related to this action. If I tropicalize this map, then as I said before, the tropicalization of this torus is just the lattice I'm working with. So this would be H dual. And here I will have like some tropical space that actually helps me to parameterize theta functions. And this lemma that, well, version of it was done by Roszak-Kilkoncevich, and maybe the version we're using that goes like beyond the schizometric type was proved in our paper, is that every function on A is an every theta function on A is an eigenfunction with respect to this action. So I have theta functions here, and I have this action, and the theta functions here are eigenfunctions with respect to this action. So they have a weight, and the weight. So these theta functions are parameterized by the tropical points here. So if I take H a base here, and I take the inverse image, I get a subset of here. That is, so a subset of theta functions. This subset parameterizes theta functions on A, and those are precisely those theta functions that have this weight H. Okay.
So where does H come
For every H. It's a weight. I mean, the capital H. Okay. Yeah. It's just so you have a freedom of choosing different matrices. You can change here. So you can change this is a variable, and this H is a variable. So it's something that you have lots of freedom to construct this H, and my theorem is going to be about this H actually. Okay, I'm almost there. So yeah, okay, I'm 3 slides. Okay, have 1 minute. I'm sorry. So first of all, let me just say which kind of compactifications we're going to consider. First of all, recall that the Picard group of variety Y is just the abelian group generated by the isomorphism classes of line bundles with the operation given by the tensor product. And the universal torsor, it's just some scheme that you can build that kind of whose coordinate ring codifies all the section rings of all the line bundles over your variety. So this spec, bold spec, is just you are gluing all these line bundles relatively to the base Y, right? So this is just a quasi-coherent shape on Y. You can just glue all of them over Y, and you obtain some scheme relative to Y over Y. And if we assume that this is peak, then the global functions on this guy is going to be given by the sum of all the section rings of these divisors of these line bundles. And since this is free, this is peak Y graded, so we have an action of the dual torus on my variety, on my scheme. So for example, if I consider G to be SLN, then the full flat variety is going to be given by G mod B, and the universal torsor is just going to be isomorphic to the base affine space that I discussed before. So the main definition for my theorem, I will say that a cluster ensemble P to M. So this matrix you should think like as defining a map from N to M. So if I can choose an H such that well, if I can choose a P star and an H such that these two conditions hold. So what are these conditions? H and this lattice and this lattice have the same rank, and this torus is acting here, and this torus is acting here, and this contains here. So I'm just asking that the action of TH coincides with the action of this torus restricted to A. Then I will say that I have the Picard property. Okay. And my theorem, our theorem, is that if a universal torsor has an AC structure and is a partial minimal model that has enough theta functions, so this comp parameterizes all the theta functions that extend to my universal torsor, and I can find a P star and an H with the Picard property, then the quotient variety Y is a minimal model for my quotient variety. And for every L, since L is in the Picard group, and I'm assuming that this and this have the same rank, well, I can just fix some isomorphism and think of L to be in the base of my. So let's say I'm just going to replace here peak Y. So I can just think that the base of my weight map is the Picard group of Y. So then I can take the inverse image of the class of this line bundle. This defines let's say some sort of hyperplane in the space that I use to parameterize theta functions on A, and I intersect that with the cone telling me which are the theta functions that extend to the universal torsor. Then this guy is a positive set, and this guy, it's the guy that reverses Gross-Hakenkill construction. Let me say it again. If I run Gross-Hakenkill construction to this positive set, then I obtain Y. Okay, so it's just, I'm just reversing this construction by building a cone and slicing it by some hyperplane. So maybe just the concluding remarks. At some point, I start talking about universal torsors. This is just to be closer to representation theory, because this is like my prototypical example of universal torsor. This guy. So there are various relations like this in representation theory, and cones associated like this, like the Gelfand-Tsetlin cone, arise like superpotential cones, and slicings of this sort recover like superpotential polytopes associated to these cones. So here I have lots of freedom to build many cones because I can change my seed. I mean, the Gelfand-Tsetlin cone will just be associated to one single choice of seed, for example. Second is that we can show that this the NO bodies constructed by Rietsch-Williams are of this sort, and this is not obvious at all. And well, putting together this with a previous result by Cheung, McGee, and myself, we can describe these Newton-Okounkov bodies as broken line convex holes. And yeah, we also address some other motivations. So just let me finish here and put my list of references here.
Yeah, I'm a bit confused in the statement of the theorem. How does the right-hand side depend on the speed?
Yeah, I mean, this doesn't depend on the seed. You can just think it like, but this does depend on the seed.
Good choice, or?
I mean, like let's say this to go to a lattice, then you map this set. You have your abstract tropical space. You choose your seed and you move to that seed. And then once you move to a seed, then you use the G vector valuation associated to that seed, and then that's the valuation you're using. Yeah, so I mean, I could have put seeds all around the place, but yeah. And maybe something that I also forgot to say, it's like in the case of the Grassmannian, there's something very interesting maybe for this conference is that, well, for this theorem, we need to find some P star and some H. So in the case of the Grassmannian, this cluster ensemble map, it's just the Euler form of the dimer algebra arising in the categorification of the Grassmannian. So there's also like some interesting connection with the categorification picture through this choice of P and H.
I had a question. In this work of Chavez and Khovansky, they showed that this what do you call it? This polytopes associated to crystals, string polytopes, arise as Newton-Okounkov bodies. Is that like also kind of recovered from?
Yeah, it is, but maybe my co-author Lara knows more about the details.
Yeah, well, the string polytopes are examples, but the weighted string cone would be an example of the cone that Alfredo has.
Okay.
In type A, like.
Okay.
And in that kind of example, what's the H? Or the
Yeah, it's like a beautiful problem to find the H. So in this case, for example, in the Grassmannian, you have to first define P star. So you have to try to know what you're going to fill here. And in general, it's not skew symmetric. It's something different. So the case that I know very well is the Grassmannian. We obtain this P star by just taking the matrix of the Euler form or some associative algebra that arises in the framework of categorification of the cluster structure of Grassmannian. So somehow that is given by a path algebra, and Cohen-Macaulay models over that algebra gives you the categorification, and it has an Euler form. And the Euler forms tells you how to fill those guys. I mean, it's very subtle because it depends on the orientation of the quiver and if you're working with K or N minus K. So I think it's the most interesting part of all the problem, how to find this P star and this H. And in that case, H is just the kernel of that map. It's one dimensional, and you just take the kernel of that guy.
Okay. So the flag right case H is the character letters of the torus acting on the flag.
oh,
Which is the Picard group.
Yeah, in this case, you kind of identify that. In that example, it just comes in your head, like in the nose, and in this, you kind of have to build the identification. Yeah.
I guess you said that H is always the Picard group. Or that's
Well, yeah, those are Boolean groups. So the Picard property asks that they have the same rank. Also, yeah. Also, you have like some preferred isomorphism or something.
Other questions? Okay, let's thank the speaker again.